tonight we're going to go through a design exploration of 2910 Jack in the Box 2025 World Championship winning robot. They released the CAD for everyone to be able to see. We can look quickly at one of their matches. This is the final tiebreaker from Einstein, just so we can kind of see how this robot kind of flows through and how it works. So here they're running the auto out of the human player station. So this robot's able to do a little bit of everything. It can ground pick up. It can human player load if it needs to. It can play the algae game. It can do L1 coral in nice clean stacks to get even more coral on L1. So it's one of the best robots in the world. Them and Jack in the Bot are probably 1, 2, and you can argue over the order. Or them and Madtown, sorry, are 1, 2, and you can argue over the order. They'll go through, they'll play the algae game. I think they cross at some point in this match, and they're just filling up the reef as much as they can. And then as we get towards the end of the match, they're going to continue filling the reef. I think we should see them play some of them down on L1. Yeah, so they're kind of behind the reef there. They're playing on L1, so they grab it a little bit differently, and then they're still able to come in and place it that long way, so they can score even more coral once the full reef is full. The branches of the reef are full at least. And then right towards the end, we can see them come in and climb. They're going to grab, and they have one of the fastest climbs in the world. Once they're aligned, they can just pull down that arm and get really far off the ground to leave no doubt that they're climbed. Okay, so I have 2 CAD models of the robot. We have the one that they published the link for that we don't have any sort of edit access for, but if I need to, we may be able to come into this model that we have downloaded in a copy, and it has some, we can move things around a little bit easier potentially. We'll see. Okay. So this 2910 architecture has kind of been synonymous with them. They produced a robot in 2023 with a very similar design where they had this rear pivot with the arm that telescopes. And so several teams sort of learned from that and copied it off and even built robots in the off season of 23 and then even robots for the season of 2024. Like 359 Hawaiian Kids built a robot using a similar architecture for 2024. And then they realized they could do the same thing again for the 25 season and still meet all of their design requirements. So they were able to get coral to all the levels, get algae all the way up to the barge, keep a low center of gravity. And with the complexity of this arm and things, it does add some intrinsically complex things that are tricky to build and things as you're going through it, but overall on the external package, it's very easy to know what's happening. One big pivot, long extension, powered wrist here at the end to be able to give them some more angle flexibility, and then the intake at the end of the arm. And so then they can build the climber right into the arm as well, so they're using those same motors to move the arm as they are to climb. So it becomes a pretty efficient package, but you do have to get everything right here, because if your arm messes up, you can't score, you can't climb, you can't do anything, right? So if your arm's not moving anymore, you're basically out of the match except for a little bit of defense or to park at the end. So you're definitely a lot of reliability, making sure you are nailing all of the design and engineering of all of this, especially over a season, especially to be as fast and accurate as they were with this robot, as it was scoring, high 20s plus game pieces, depending on if you're counting auto or not. They were scoring a lot of game pieces per match. Okay, so let's look at their kind of mechanism breakdown. So they do this basically the same thing we do when we break down the robot. They have a drivetrain, they have the pivot, we see their climber mechanism, we see the arm, and we see the intake and wrist. So they drop their robot into 5 mechanisms, very similar process to how we do it. So we can go ahead and isolate our drivetrain here, and we can see what they consider the drivetrain. This is a pretty standard drivetrain. This is the model before they changed to the MK5 prototype beta modules for the World Championship. They're still running the MK4Is, the same swerve modules that Spectrum ran for the last several seasons. And so nothing too complicated here. They're, yeah, pretty standard Kraken steering, Kraken turning, and MK4i modules. Electronics are all on just a normal belly pan. They don't have a ton going on down low other than some motor mounting for some of the other mechanisms. So they have room for their network switch, for the radio, for the main breaker. They were running the CTRE PDP 2.0. So they have that PDP here as well. Here's their battery connector and battery. They're still running the SB50s. They didn't transition to the SB120s. Again, that's not a place where performance really changes, so teams can get away with that and save some money by not doing the swap. Have their RoboRio mount. I believe they started doing all of these in TPU, so this is like a TPU housing that wraps around the RoboRio, so it seals out dust a little bit better than some of the other things. So like metal debris and dust and things don't get into some of the cracks because they have this nice TPU mounting. It probably does a little bit of shock mounting and things as well. And then the canivore just right on top, double-sided tape, VHB taped, similar to how we normally mount ours as well. Battery doesn't seem too complicated. Little TPU shell printed for it, and then some way to get a battery strap up and around through like this hole and through this hole. Yeah, it looks like what's happening there at least. I don't entirely know where the other side of that strap goes. It may just go under. Let's see, sometimes if we, yeah, I don't entirely know where the strap goes. Oh yeah, probably under and then out through here, up through there, and then back up. Maybe not back up, maybe just around the battery there. That's fine. So relatively simple there. Bumper mounting, they have a few different bumper sections, so they ended up doing 2 outer Cs and then a middle piece here. I'm not entirely sure why they would have had that extra cross section instead of just doing 2 Cs, but we can see some of how their bumper mounting works. It looks like there's a standoff here that's going to be bolted in from the bottom, and then this bolt is what bolts through there. I don't know what that is. I don't know if that's just spacer or if that's some sort of potential rubber. Let's see if it says anything. That's just a replicate. But really doesn't say what that is. Yeah, I'm not sure what that one would be. Oh yeah, so some type of aluminum spacer most likely. So then this is what they're able to bolt down to get their bumpers on and off. Something like that it looks like. If we move, oh, that's just forms. Oh, their bumpers aren't. Oh, they have the whole bumper assembly. So we can remove the whole bumper assembly and see where we have some of those mounting points. So yes, you have the mounting point there, there, and there. That they're basically just bolting down into to take their bumpers on and off. There might be a way to capture those bolts inside the tube. I'm not entirely sure. Since that nut is there, since the nut is here, that bolt can't come off. I don't know about this spacer, whether it can come off or not, or whether that's actually there in real life. But the bolt is captured, which is pretty nice. You're never losing the bolt. And then you can still just turn it down and bolt it into here when you need to. Okay, I don't think we need to spend too much other time on the drivetrain. Everything else looks pretty stock standard. They have some amount of a drop, like basically everybody these seasons, these last couple seasons. Yeah, probably just using, oop, clicked the button too many times. Yeah, this is probably just the SDS standoff. Yeah, so these are the ones that SDS sells that drop you an inch or a little less than an inch. I think they're like 3/4 or 7/8 or whatever that is. Yeah, like 7/8 ish, whatever that is. So we normally just use a tube here and drop an inch. It just depends on how close you want this plate to be to the ground. It doesn't really matter as long as it's a flat game. You can kind of do however, you can scrape the ground as close as you want to if there's no cable bumps or anything else in your way. Okay, so relatively standard drivetrain. Oh, the one thing we did not discuss is this yellow bar up here. So this is their brass bar. So this bar is very dense. It's made of a brass 2x1, so that whenever the arm is up out the back and has all of that weight way out here, you can have this rather large bar giving you your counterbalance. So it's like 10 pounds just in this one 2x1 on their front rail. So that robot is going to be a little bit more stable when they move the arm back really, really fast. It's probably not going to tip as much as if the ballast bar was not there. So we've done similar things with weighted plates and things. We haven't done a full steel or brass bar yet. But if we ever have the weight and we need to pack it in there, this is an option to replace one of the frame rails with something a lot more dense to get that weight right where you want it. Okay, so moving up from drive base, we can go ahead and get into pivot. So their pivot is definitely a little overpowered, but it's also able to be. Like, they have the motor slots for it, they have the weight for it. So it's not really a problem for there to be three Krakens driving the pivot. Sorry, three Krakens driving the pivot. I believe this side is the actual pivot. And then this side gets transferred to the extension, I believe is how it works. So we'll go ahead and look at that here in a second. So yes, they have all three Kraken motors just kind of lined up in a relatively standard way to do the gearbox. This gear right here is just the idler. This just allows you to transfer the power from this third Kraken over to the main gear here that's actually driving the rest of the mechanism. So that's these two are attached to. And since this is all in line, you're not getting a ratio change between these. This gear just does the power transfer going on over, so relatively simple. Everything's done with just bolted standoffs. They have their plates tapped, so they're able to not have to worry about like nuts on the inside of this. So if you're doing assembly or disassembly, it's a little bit quicker. You don't have nuts falling into the robot, or much harder to get a wrench into places. Being able to tap these plates make that a lot simpler. Most all of this construction is 1/4-inch aluminum. I know a good amount of their things are 70-75. I don't know if all of it is. Some of this might be 60-61. But like out when we get to their intake, I know all of that is 70-75 from things they've posted and things I've talked to them about. So 70-75 is just a stronger aluminum that's a little bit stiffer most of the time. It's harder to bend it, and so it can be a little bit more durable than 60-61 that might bend or even like crack sometimes under certain stresses that 70-75 won't. Okay, so you have the arm motors here all driving this gear. This gear shares a hex shaft going all the way through the robot over to that one. But if you look, how does this work? So this gear is on bearings, so it's not actually mounted to that hex shaft, where this one is. So that this gear and this one are powered off the same shaft, and you get that host of stability of that shaft going all the way through. But you don't have another, but this one's going to be separate because it's going to actually power their extension. Okay, so we come up here, we get another gear reduction, so we're reducing a lot because we need that arm to spin pretty slowly. Like it's never actually doing a full revolution. It's only going from collapsed to a little bit past vertical when they score on the opposite, when they score like L3 and L4 over their back, or all of the whatever they score over their back. And so we come down to another gear, and then we have a sprocket here, which I believe this is all 35 chain. normally look through and see. Yeah, so 35 9-tooth sprocket, so a relatively small sprocket. 35 chain, so nice and big chain that you're not going to worry about it snapping under load or anything. And then with any sort of chain mechanism, you always have to figure out how you're going to put in your tensioner. And so they tension off this device here. So they're able to have a static rod running across this frame. Then they have a couple places where they have bolts. And this assembly, so this extra gear and gearbox plate, same with this one, aren't mounted anywhere. They're just mounted on these bearings. So this gear, this sprocket can all pivot. And since they're pivoting around this gear and this gear, as you tighten these bolts, you're able to stretch this chain further and you can tension your chain. So if you didn't have this, as you use the robot over and over again, the chain links in here would start to stretch a little bit, and you run the risk of them potentially skipping a tooth or anything like that. And so by having that chain tensioner, you can always increase tension just by tightening these bolts, and they don't even have to be the exact same. This one can be tighter to tighten this chain, and it just moves this gear around the other one, and then you can tighten this one separately to move this gear around here and still provide the power you need out to the actual arm. Okay, the other side is pretty much the same thing. You're just going to have a little bit of a different ratio because the extension has a lot more travel on it, right? It's pulling a lot. It has to rotate a lot more distance to be able to do the full extension compared to the arm, where you need a lot of gear reduction. So you can see you have a little bit of a smaller sprocket here, doing the idler path all the way between them, driving this one gear here that has, again, another small gear reduction. So you're going a little bit slower up to here. As we go small to big gear, we're getting a little bit slower. And then we do it again. So this gear actually just acts as an idler, as you're really getting the gear reduction from this gear up to this one. And then that one is driving your sprocket, what's going all the way out to a sprocket up on this hub here with this gear. And so we'll look at that in just a second. Okay. The other kind of details that they placed into Pivot, we have these like 3D printed, I'm guessing TPU mounts so that the arm can come rest in them when it comes down. You get a little bit of shock absorption there. You don't have like aluminum touching aluminum. They're able just to bolt these into this plate. To mount this plate, they're just using some nut strip here. So you have some bolts going through again. So that's one nice way to get some 90-degree connectors off these plates, so you don't have to like edge tap any of these plates anywhere or do any like laser joints or finger joints or anything to be able to get that 90-degree connection. And then it's just 2x1 going up. And they have some places to be able to bolt or rivet. I'm not sure which ones they chose to do there. In real life, it probably is rivets because they seem to have modeled most of their other bolts, so these are very likely rivets. And then we have all of their limelight mounts. So they were running 4 different limelights so that they could always see the target no matter where they were aligning to the reef. If they were off to the left or right, they'd have one. They would always have a camera being able to see it. All relatively angled similarly, so relatively easy to do the positioning and math and everything to make sure your localization and things are all working. Inside of 3D printed cases, just coming off these tubes. Relatively easy to do. We got some other details. They got a signal light in there somewhere. They actually made a nice little hole for it to be able to mount their RSL. These guys are LED strips that they have in CAD so they can see all the driver feedback and things they normally would get. And then some other rear mounts down here for things. What is that? So we got a spring here and a bar. Oh, I know what this is. So this is tricky to see in CAD, but a lot of times when you have things like this is often what's called like a kickstand. And so see if I can see the easiest way to do that. When we go into our stowed configuration, and if I can bring the drivetrain back. All right, so this whole arm and everything is fully outside frame perimeter, so you can't start a match like this because you can't start a match outside frame perimeter. So that means they have to start the match with the arm up. And so I believe if we go into starting config, yeah, there we go. Okay, so we can see we have this little bar here that's mounted to the stationary rail. There's a spring here, and so that's sprung to this hole probably, something like that. And so you're able to, basically with the robot powered off or whatever you need to do, move the arm up a little bit, pull this bar out until you can get it to slot into this hole they designed into it, and then rest the arm back on here, right? So as the arm is pressed here, it can't fall down any further because it has this whole, it has this piece of aluminum put into tension, it's pulling on it, and it's supporting the weight of it. So it's starting up in a very known position, so they're able to know their encoder positions here, they're able to know the starting location of the arm, and then always know they're fully inside of frame perimeter. Then as soon as the match starts and they go to score their first coral, the arm swings further backwards, which it's able to do, right? This isn't stopping it from swinging backwards, just from swinging down. And so it's able to swing backwards. This gets pulled out of the way by the spring. And then we're back into just useful arm motion, as this is just down here hanging out above your PDP without getting in the way of the arm the rest of the time. So it's just a nice clean way to always be in starting config, know you're in starting config, without without having to have the motor set in brake mode or anything else specific like that. Okay, I think that's most of the pivot mechanism because they're really just those two, again, relatively simple gearboxes. They're nothing too complicated. If we need to do the same thing, you could design these plates in a couple hours and be pretty happy about where you end up. Getting the full architecture right is a little bit trickier, but this is not anything too complicated to build or design. Some of these parts are a little tricky if you're just doing 2D manufacturing. So if we're trying to do these on like the laser, some of these parts get a little bit harder. But there are ways to do things that are similar to COTS. Some of the chain tensioners, some West Coast product sells a couple things that are similar to this that we could make out of, that we could make it used or get something very close. Also, even if you had to make these even by hand after laser cutting or water jetting or something, you could figure out how to drill in the holes at the different angles and stuff relatively easily if we needed to. With some jigs or some 3D printed jigs or something like that, we could make these parts not too complicated. It wouldn't take too much. You don't have to do this on a CNC mill, but you could. Okay, moving along. Climber's next on theirs, but we're going to go ahead and do that after we do arm and everything else. So let's go ahead and look at arm. Okay, so this is definitely where the robot gets the most complicated and also the place I know the least about. So we can all learn together and figure out how this arm works. So the easy part is the pivot, right? We have that chain coming from the pivot gearbox, the shadow chain right here, going up around this sprocket. This is a custom sprocket they made, I believe. They just CNC'd and cut the teeth into and then chamfered and everything. And so that gets bolted into their main arm plates, these large plates here. And so that's what's really transferring all of that torque and energy from those three motors and doing that pivot whenever it can. It does like kind of separate it off so they have some room for some things like that climber to come in, or for where they have the string here that they use for tensioning. We'll get to that in a little bit. I think that's part of the climber too, I'm not sure. And then, so none of that's contacting or anything, and they can just have the chains spaced off a little bit further instead of having it directly there, because otherwise the chain might touch like this gear or anything else that ends up right on the side of the arm there. I'm gonna unsuppress that so we can see the whole thing. So yeah, so you can see the chain come around. You can see it not make clearance for everything, so it's kind of spaced off into its own place without touching any of these other parts of the robot or the arm or anything. And I believe these are all just long bolts. Yeah, so they just have long number 10 bolts going all the way through with those aluminum spacers spacing off these main plates. Which again, oh no, these are actually a little bit bigger. So these are slightly bigger than quarter. So I think these plates get all the way to like 5/16, 5/8 even. Yeah, that's 5/8. Wait, 3/125, whatever that is. I'm not doing the fraction right now. It's coming back from the off season. It means my fractions aren't as good. But these are definitely thicker plates than the quarter they were using in other places. Okay, so let's see how they actually do their extension. That is the part that is a little bit trickier. So we know that the motors down here are doing the extension. So you have these 3 motors, chain coming up to here. And now we have a sprocket bolted to this gear. All of this is on a very large pivot tube that we actually haven't talked about. So I take it back. I'm not going to talk about the extension yet. We're going to talk about the pivot tube. So pivot tube, what are they doing here? So we have these plates, and this is what's actually mounting the pivot to the rest of the robot, right? It's mounted up to this these A-frame posts they have. You have it mounted into there. We should be able to see. Let's see. We go into pivot. Yeah, so they have these plugs, and then they also have the main. Then part of it is arm. Okay. So if we isolate on pivot again, yeah, so we can see that these pivot points are machine parts that are a little bit different than the rest of the arm, and so this allows them to pull the arm off easier because they can basically unbolt this really long bolt that's running through here, pull the little caps off, these machine parts that they have here, and the whole arm can just come off through the middle, and they're not having to like push a shaft out of bearings or anything along like laterally out the side or anything like that. So everything's mounted in these this super fancy part that they're able to make. This would definitely be a tricky part for us to make with our machining. Let me isolate that alone. There we go. So yeah, so you can see what this looks like. This has to be out of a pretty big piece of billet, I think is how they make this. I don't know another way to do it. So it's very likely a piece of at least 2 5/8, potentially larger piece of round aluminum stock. And they go in and on some sort of tool. You could probably do it on a manual lathe if you really wanted to, but it's very likely to on CNC. They go through and set the different steps here that they need for the part on the outer shell, and then also come in and hollow and bore out the inside to a few different steps as well, along with boring that hole through the middle. That's my guess at how it's made. Could be made some other way. But this, like, if we want to design a part like this is also a way that you could, outsourcing this isn't too difficult. It's a lathe part. You could make a test one, you could print a test one and have it working well enough for a while. Like if we needed to print something to hold this up, you'd probably make it a little bit more solid, but you could probably print this for a while and get away with it, maybe even a whole season. But if you wanted to make a printed part and then have an outsourced aluminum part made, it wouldn't take that long to have someone make that with a lathe, or have it be machined by one of the outsourced companies. Is definitely doable. Okay, so that's basically what's happening on both sides there to be able to mount their large pivot. And then when we go in to actually see that tube, we can see what it's running on. So then that is basically compressed into this much larger machine tube as well that you can see the steps on here. They have a smaller OD where they're down to like 2.5, and then they have a larger OD where they're back up to that 2.625 number. And then they have certain things being able to ride on that. So you have the bearings. If I'm not isolated, you can see the bearings here. So you have the bearings here that have that 2.5-inch OD, so it's able to slide over this and then get stopped by the rest of this tube. It'd be relatively easy just to run a 2.5-inch diameter tube the whole way through this, and then put something else here to locate it. So you could do like a snap ring groove that potentially makes things a little weaker. You give some points where it could like crack, and then you still have to do some things on the inside possibly to hold where it's going to be too, because they still have this shoulder here, which you could in theory do with like an internal snap ring groove. Those are things you can do. They just are potentially trickier to maintain or trickier to machine, and potentially maintain too if you have to take the snap ring out or anything. There's also a very large snap ring on either of those, but they do sell them. Those are things that you can get. But you may need even bigger snap ring pliers to be able to put them over something like that. Then some other parts here that look probably 3D printed. Be my guess. I'm not entirely sure. And those are all, so yeah, so you have the whole tube is able to, the whole arm is able to spin on the bearings on a stationary tube here. So that tube is basically acting like a dead axle, while the arm and these plates are spinning on the outside of these bearings. Okay, so that's how their pivot works basically. Again, not a lot of parts, relatively simple if you have all the parts to put it together, but definitely takes some work to design it the way they did, and figure out all the features that are needed to make that assembly easy, so that they can just take those two end caps off and remove this whole arm assembly, and swap it entirely. Like if they had to do that between the matches, they could. I know they had a spare full arm assembly. Okay, so there's a few more bearings in here because you have to have, since this sprocket and this gear aren't attaching to the arm itself, they're driving other parts of the mechanism. These all have to be riding on bearings, so they have these same bearings inside of here that like the whole arm is riding on. That when they power the extension, it's able to power this sprocket and then power this gear that it's bolted to. So I think we can kind of see that here. That yeah, so they have all of these holes are just tapped for the bolts coming in. And then we can see the rest of that motor power goes from the gear to this idler gear and then down to here. And then that's what's driving our sprocket assembly and our sprocket shaft down here at the base of their arm. All right, so let's look at some chain path real fast. So we see we have, as this were to spin, you can start pulling on this chain. And so when it pulls on this chain, it pulls up to their chain tensioner up here. And so it's moving this whole, like this black assembly is going to be pulled down to do the extension. And then on the inside of the arm is where it gets a little bit trickier to see. We should have something in here. Let's see if we can hide some stuff to show us that. Let's see, there we go. So we have this assembly here that they made. And so this is what bolts to their first moving stage of their extension. So you have this plate, has a couple screws in it, and it is bolting the chain to this. So as you pull down on this back side of the chain, this front side moves forward and does the first part of the arm extending. And so we can see some of that, and kind of how they're able to make that work. So that's very, very similar to just a normal cascade elevator or anything like that, where you have that loop of chain. You pull down on one side and the other side goes up. And so they're doing that twice though, so they have both of those loops of chain here, so there's some redundancy there. So if something were to happen to one of those chains or something, it's very possible they could still extend the arm as long as one side is working. So if you do get some damage somehow, if a chain breaks, you might still be able to get the arm extending, which would be great. And then when we go through the next stage is where we see how the cascade works, I think. So the blue and, or the purple and green lines, I believe are part of climber. I think, maybe not. Maybe those are arm. Let's see. Where'd that plate go? Okay, that plate's there. So this line is there. That's coming up and over. Oh no, that is part of arm. So I think that is part of the cascade. Okay. So let's see how all of that works. So this is tied in. So the end of this line can't move. So this is tied into the plate that just pivots. The other end of this line is something we can kind of figure out in CAD somehow. Let's see if we can see where that goes. So that goes down into here. So let's see where we're at. So we have our here. Okay, so that's our external tube. So this face right here that I'm clicked on is the one that doesn't move, right? So that doesn't extend. That's just your main stationary part of your arm. I'm going to hide that again. And so now we have the other part of our arm in here, and that's the part that moves with the chain stage. So then I'm going to go ahead and hide that part of the arm. I'm going to clear out some more things so we can find some space in here to see things. I'm going to hide the chain. We already talked about how that works. And now we have our green and our purple rope lines. And so since this is tied off and stationary, the top of it goes over the pulley that's mounted to the second stage. So this pulley and these this pulley up here, these bearings, all these plates, these are all part of the stage that gets driven by the chain, right? So this chain moves this whole assembly out. And so as this pulley goes up, and since this rope is stationary, it's basically pulling down again. It's pulling down again right here and causing that inner stage to go out. So this is what we call a cascade, because as the first stage moves, as this first stage moves here, this one has to move like the same amount because this is moving up an inch, so it's pulling that rope up an inch. And then we can kind of see the down line as well. We have a purple down line that's attached here to that stationary spot in the same way. And then it runs through here. All of this is going to always be stationary, right? Because this cord length isn't going to change except when the tensioner changes, except when we apply tension. But it's not going to be moving, so you're not worried about like the rope rubbing through this little cutout or anything, because that's not moving during the robot operation. Only the stuff past here is able to move up and down. This length is always going to stay the same, since all of this is part of that stationary stage. Okay, so then we can kind of see where the end of the purple line goes. It's coming all the way down here. All the way down here, and then it's on a pulley that I believe is part of that first moving stage. Yes, it is. Okay. So that pulley and these bearings are all part of that first moving stage. So similarly, when the green line kind of pulls down to pull the last stage up, the purple line is extending out, and then when you pull back in, that purple line pulls everything back down to pull this inner stage down with the arm. So we end up with a two-stage extension. You have your first stage that doesn't extend, or you have your stationary stage that doesn't extend. You have your first extending stage and your second extending stage. And so the second extension is done cascade with rope, and the first extension is done just with a chain loop. or in this case, 2 chain loops for redundancy. They only have 1 string, though, on this stage. So if that string were to get cut, you wouldn't extend anymore. If that green string gets cut or snapped or something happens to it, this part of the arm wouldn't extend any longer. Things I'm not going to go into too much detail because they're kind of all similar elevator telescoping arm stuff. You have the bearings here on all 4 sides of each of the poles. So these ones are on the first extending stage. So these are like at the top of them. And as this goes up, the aluminum tube rubs against all of these and rolls to allow this to go out. And then down at the bottom, where we were looking at before, you have your 2 sets of those inner ones that run with the stages going up and down. And they're riding on the inside of the previous tube, allowing it to have nice smooth travel as well. And so a lot of these are tricky parts to make. So I'm guessing these are all CNC machined. This is definitely a tricky part. A lot of teams have made similar parts to this just by 3D printing. So there are ways to do this. They've also done this assembly as multiple parts instead of a single part. It just kind of depends on exactly how much space you have and the design materials and machines you have to actually make the part out of it. But really, you're just trying to get all 4 faces riding on bearings. In this case, with the jack in the butt arm, your front and back loads are going to be a lot higher because that's kind of the weight of your the rest of the arm and everything as it moves back and forth along that arc. So they have 2 bearings on the front and back, and then only 1 here on each side, distributing that load. Because there's going to be less side loads as the robot's driving around compared to those front and back loads. All right, so I think that's most of that assembly. There's probably some stuff I missed. Again, like there's a lot of detail in all of these machine parts. Like you could sit and look at a lot of things in here, how they have like different standoffs or plugs to hold it into where the arm is, kind of locate everything. Okay. Before we go to the intake, we can look at the climber pretty quickly. So their climber is partially powered by their pivot, right? Because it's going to twist or it's going to turn down and pivot when they want to climb. But they also have a Kraken X44 driving their wheel captures. They have these latches here that hold on to the pole. Oop, I rotated a little fast. All right, there we go. They have these latches here that get sprung right here. So they have a spring connecting these two, so that as this gets pushed in, it's able to like expand the spring. And then once the bar goes behind both these latches, the spring pulls them back closed and latches the bar of the cage right in that little loop. So again, relatively easy way to do the capture. It does take an extra motor, but you do get some advantages of having it powered, so that if the cage were to hit somewhere along here, it still tries to drive it in and drive it into that gap. And then the other part of the climb is the motor that's back here, driving this other chain mechanism. And so that sets where this is, as this outer carriage basically rides along the outside of the telescoping arm part. Yeah, so you can see here, you have these bearings riding up and down these rails, and they have these plastic sliders built in right here. Instead of bearings on the side, they just have some blocks to be able to slide up and down, probably made out of Delrin, which is like acetal. It's a plastic that's super slippery. You could also make it out of like PTFE, anything where you're just trying to reduce that coefficient of friction so it can slide against the aluminum easier. Again, most of the robot weight is taken on that front and back direction, so you want that to be roller with these bearings. But then if you have to use static friction here, you just want some material that's going to reduce your coefficient of friction the most, which in this case is some sort of slippery plastic. You could probably also lubricate this a little bit. I imagine I don't know if they did, but they could. You could spray this with some sort of lubricant, and that would make it slide a little bit easier as well. And so similarly, they have a chain tensioner here, so they're able to tension that chain and make sure it's ready to go for every match. And then they go and grab the cage, raise this up, pull the arm down, and that's the climb mechanism for getting it off the ground, which I think they might have somewhere in here. Yeah, so you have like climb lock into here. Oh, actually, that is one thing I forgot about. So in here, when you go into, if I put bumpers back, I think is what I have to do. Bumpers back. They have this big pocket. Um, this arm actually, when it's folded down, is a little bit farther back, right? You can see it retract a little bit here. When they go to lock their climb so it can stay up after the match, they extend the arm just a little bit, and these little tusks, or whatever you want to call them, go into this 2x1 that's on the back of their bumper, and it locks in so that the whole arm can't unfold. Oh, they even added in the cage for you, so you can see like their climb position there. Might have got which way they climb backwards. They start up. Oh yeah, so they climb starting up. So they grab it at the top, pull down, rotate back, and then lock it. So I think I did that backwards, or I set it backwards. So that's their climb position, and these are all just relatively normal plates. And then this is a large box tube section. Yeah, like a 3x3 or 3x2.5 or something. 3x3 box tube in there to give it some strength and to connect the two plates, to connect everything around there. You could potentially do this with just like nut strips in the corner or something instead of having the box tube, but you definitely get a little bit more strength with the box tube. All right. So the last bit, because we are getting close to the hour, but I think I'm going to be pretty close to getting this done in under an hour, is how their wrist and intake works. And this is definitely probably the most detailed part of the CAD, where you have a lot of things all kind of sharing space and figuring out how to make everything work together. There are 4 motors all right here, right? We have the 3 X44s and the 1 X60. Starting back here at climb, we can see we have these plates mounted directly to the extending arm. And we have these big plates with bearings on them, and these large sprockets here that are kind of built in to this larger stationary wrist mechanism. So let me see how I can see what's inside this. Okay, so yeah, so this is almost certainly a 3D printed part, right? You're not making that shape any other way. And so we're able to kind of match this to the end of the arm tube, get it to bolt in there and secure it really nicely. And then as we look through some of the other parts of this, yeah, we can see this gets able to be bolted through all of this and the sprocket. And if I'm not mistaken, it's all bolted. Yeah, it's all bolted straight through this plate, through the 3D printed part, through the sprocket, through the middle and everything. So that means these two sprockets don't spin in relation to these plates, right? They're completely static. They're not rotating because they're fully pin bolted through into those places. And so what that lets it do is you have this hex shaft that's running through it, and it's not actually, this hex shaft doesn't contact the 3D printed part or the sprockets at all, right? So it's just running through air there and is able to rotate through these bearings without interfering with any of that stuff. So then how do you actually get motion if you're not spinning the sprocket? And so what you do is you have the motor that spins it mounted on the arm, or mounted on like the intake itself, not mounted on the extension. And so that allows you to have this motor, when it spins some stuff, you're basically going to move around and pivot the intake without moving that sprocket. So we can kind of look and see how that's going to happen here. We have our motor. That motor should be driving a gear that I put somewhere. There it is. All right. So we have the motor pinion here. It's driving this gear. That gear is on that hex shaft that's going all the way through this. So that means it's coming out and powering this sprocket way over on this side. So now you have that motor powering this sprocket. It goes up and gets reduced. So you get another gear reduction to a pretty large sprocket here. Along with this sprocket here that's going to act like a tensioner. We'll see how that works in just a second. And then that same shaft, now that it's spinning even slower, right? We're spinning slower here. We go to a small sprocket to a big sprocket, spinning even slower. And then along this shaft, we go to smaller sprockets again. If I had to guess, I'm guessing these are all 9-tooth again. Oh, nope, these are 12. Okay, these are a little bit larger than the ones we used earlier. So these are 12. And these go back to 2 chain runs that run along those stationary sprockets. So whenever these rotate, the whole wrist moves around these sprockets. And so that's how they're able to get their wrist angle by having that sprocket stationary. Okay, so to be able to tension these chains, they have to do a very, not necessarily very unique, but just an interesting thing in which you have to tension all 3 chains with the same shaft. And so they have these cams here. And so these get bolted in from the outside. And they have basically, they're threaded. And they can loosen them up and then tighten them to have this can push down on this shaft, which is going to push harder on this chain, push harder on this chain, and then this side too to push harder on this. So you can dial it in and get pretty exact chain tension or enough. And then with so much chain wrap here and here, you really have a lot of margin of error for where you need this tension to be to not have it skip, because you have so much of the chain engaging all of those sprocket teeth. The odds of it skipping are very small. Okay, so that's how their wrist works. Going a little bit further, we have their intake. So they have 3 motors on the intake. You have the Kraken X60 and the 2 X44s. Each of the X44s is basically driving a mirrored assembly, one on each side. That's just a relatively simple gear reduction. You go from motor pinion to a large gear, another small gear to a large gear that's just on a hex shaft driving these 2 4-inch Andy Mark compliant wheels. You do see some of that same plate construction again, where they have the plates and the nut strip allowing them to mount them at 90 degrees to each other. Coming through this, it looks like that's probably a 3/8 hex shaft inside of here. Looks like it. Ooh, if I could click on the right face. Yeah, so that's a 3/8 hex shaft. So that probably saves a little bit more weight, being able to be 3/8 there instead of half. Yeah, so those are 3/8 wheels there for that. And those are just standoffs down to this lower plate to make sure you have nice bearing, nice support for this outer wheel and the inner wheel. And then they have a place basically between those wheels for the coral to sit and kind of gets aligned exactly where they know where it is. And then for coral intaking, they actually run 4 different sensors up here. So they have 4 can ranges, which are basically just like distance sensors or proximity sensors that can tell you if something's in front of them and how far away they are a little bit. And so as the coral's coming in software, they're able to kind of change things a little bit to decide whether they want to spin both of these in the opposite directions to suck the coral in through here. And they also use the top roller here to help guide that as well. So when this is spinning in, it's able to drive that coral in, and they can know how far to send it based on these measurements as well. So they can know like how far to hold it and when to stop the intake. Because if you just ran this intake forever, it would just spit out like they do to score, and that's not what you want. So they're relying on those sensors to stop the intaking process. But they can also use these side ones as they're going to intake the long way. They're able to use this roller and some of this willpower to be able to hold a coral um, the long way and kind of grip it between this roller and the sides here without spinning it actually inside here. And so that way is probably going to have to see how it works in software, but they're doing something to be able to kind of get that kind of centered every time too and get a good grip on it to be able to score L1. Then the algae mechanism is probably the simplest. It just has an X60 motor here, so pinching the algae takes a lot of effort. So there's a lot of current and motor power involved. So they left a large motor here so it can handle the heat of just being stalled for a very long time holding the algae. Um, it does help if you just score the algae faster. You don't have to hold it as long. So them being as fast as they were and as good as they were at the game meant that their motors didn't necessarily see as much current as if you were slower and you were just holding the algae for a longer time. Again, similar concept everywhere else, nothing too complicated. They have a motor powering a gear, driving a shaft out to a sprocket to power this lower roller, and then this back side gets extra gearing out to this belt or this pulley that powers the belt out to their top roller. So again, nothing too complicated, but they didn't have to do everything. They had to reverse it some way, so you get these two gears here that do the reversing. So this roller is always spinning the opposite direction of this one, and they can pinch in the algae very nicely. And that's pretty much the robot. Yeah, as you can see, they're kind of standard build techniques is just to use 1/4-inch aluminum plate, get it as fully skeletonized, lightened as they can. They have some big machine tubes in places where they're doing full lightning. This is often called like some version of isogrid-ish triangle lightning patterns through all of their tubes and quite a few of their plates to get everything underweight enough. I know they did have some weight to spare because you have that brass bar up there, so if they needed to get some weight back, they could either mill out part of that brass bar or replace it and get several pounds back. But by integrating so much of the robot into a pretty small amount of space, you lose a lot of the you don't have nearly as much weight to be dealing with there. All right, I think let's see up to yeah, so you can see all the various different positions inside this CAD if you go through and play with it. You can see they do have some amount of L4 forward and backward ability. They have barge ability. They have quite a bit of extension because they were able to mount it to where it's all the way over by the time they actually, when it is fully flat. So this is a much longer tube than you'd be able to make if you just had it fully flat at the start of the match. So they're able to get a lot of height out of this. Entirely sure how much. Somewhere in the see, yeah, so you're like 6 feet plus, like 6'3" up to somewhere in there. That's min distance, max distance, yeah, like 77. So yeah, like 6'5", somewhere up there. Plus you still have the wrist that can flip over and everything. So a lot of extension, even more once you're into full algae barge scoring, because that the net scoring flips your arm all the way up, so you're really tall once you go up and do that. So they're able to score algae very easily, so they get a little bit of an advantage there because the algae is even higher than the coral scoring. So overall, just a really well engineered robot, but definitely does have some parts that would be tricky for a lot of teams to machine. I know 2910 does a good amount of outsourcing of a lot of their machining, almost all of it, I believe. And so those are all possibilities, but then a lot of this you can do in plate or stacked plate. Some things you could do with 3D prints. There's other ways you could make a lot of this robot and still make it very, very successful with whatever resources our team has or your team has, whoever's listening to this. All right. I think that wraps us up for the day.